In previous videos I explained how to build an analog pointer instrument using a stepper motor and a digital filter. Today it's about a few tricks to tune the digital filter and about a vivid demonstration of the pulse response. We touch the holy grail of filter theory, so to say. I put quite some effort into developing a stepper motor controller that can be realized with Arduino boards. The stepper motor drives the pointer of an analog display instrument. A digital filter is sort of harmonizing the pointer's movements. In this way we can give it dynamic properties that it actually doesn't have from its own mechanical properties. For example, we can use it to simulate a light and nimble pointer, or we can simulate a heavy pointer that moves very sluggishly. In addition, we can dampen the movement of the pointer to a greater or lesser extent. If you want to display dynamic signals with the display instrument, then it looks much nicer when the pointer performs harmonious instead of stuttering movements. The digital filter is part of the Arduino code. And we have seen in the earlier videos that we can adjust the two parameters, resonance frequency and damping, separately. By the way, in the download area I'm offering different code versions. You can either set the filter damping and the resonance frequency in the code, or there is another version where you can change the filter damping and the resonance frequency during operation using potentiometers. Today it's about some tricks to tune the digital filter so that you get the desired effects. So you either use potentiometers or you set the values in your Arduino code. I'm working here with the version where the values are set via the code. Instead of multiple filter coefficients, we only need to set these two parameters. By the way, I have developed an Excel tool that can be used to simulate all of this, just in case you want to dig a bit deeper on the filter. A few practical tests have shown me, however, that it needs a systematic method to tune the filter parameters. That's why I'm going to give you a short step-by-step guide. In the first step, we set a low damping corresponding to a high filter quality. That means that our pointer will overshoot like a pendulum before settling to a new value. 0.5 is a good value for this. We now want to know how the pointer reacts to short pulse signals, so I tap on the microphone. A communications engineer would say, "Hey, this is the so-called pulse response." Just by the way, in science and technology, the pulse response is very often used to assess a system, be it an electronic or a mechanical system. We see that the pointer deflects and then oscillates around the 0 point a few times. In reality, this is actually the pulse response of our digital filter, and I think there is probably no better way to demonstrate it. For my perception, the pointer oscillates a little too quickly for its relatively large size. It seems more appropriate to me to reduce the resonant frequency to about half. The pulse response again shows us the effect. The pointer now swings back and forth rather slowly. By the way, you can see the clipping very nicely here. Even if it looks like it, the pointer does not run against a mechanical stop. The clipping subprogram in the code implements the clipping both below and above the scale. I think the lower resonance frequency suits better, but that's really a matter of taste. Incidentally, with that we also define the maximum fluctuation frequency that the pointer can follow. In principle, our filter is a low-pass filter that only lets low frequencies come through. For an audio level meter, for example, it makes sense that it can follow the rhythm of the music. Okay, once you have found the right resonant frequency for your application, let's move on to the tuning of the other parameter. Actually, I should say the filter quality instead of filter damping. If you increase the filter damping, then the overshoots decay faster. If you set them smaller, they decay more slowly. I set the damping so that the pointer just no longer overshoots. This is the quickest way for the pointer to reach its target value. And then I have another 2 tips for experimenting. First, you can also generate a square wave signal in the Arduino code, which is also suitable for tuning the parameters. Second, if you set up the device with potentiometers, you can use them to demonstrate the effect of the resonant frequency and the filter damping very clearly, because you can use them to change the settings during operation. That would be particularly interesting, for example, if you want to study these things further. It has really become a stylish and cool gauge, and I will certainly use the principle for other applications. Simply because it offers great opportunities for hobbyists, in particular if you want to design a dial yourself. I designed the housing in such a way that it can be exchanged very easily. I published all the building instructions for it. Maybe one of the next projects will be a nice weather station that I have in mind. And I'm also thinking about new designs for the casing and other control methods for the stepper motor. For instance, I want to achieve maximum speed of the stepper. So subscribe to the channel and activate the bell. And don't forget to leave a like. As always, have fun with building and experimenting. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.